So welcome to part two of our review of complex variables. Again, this review is intended for the benefit of my students in ECE 3337, and this course is about signals and systems analysis. This is the second part of a three-part lecture series that I've recorded. The first part covered the basics of complex algebra, and in this part we're going to talk a little bit about complex functions. Now in part 3 we'll talk about how to do a little bit of calculus with complex variables. Now in this part we're going to introduce the notion of complex zero and complex infinity. We're going to talk about some common kinds of functions, i.e. polynomials, ratios of polynomials, exponentials, logarithms. And these are the kinds of functions we're going to be using a lot in this class. We'll of course be using the sine and cosine functions a lot as well. Now, of course, the magic formula, the most beautiful formula ever that relates all these things is also something that we're going to be using all the time, and this is Euler's formula. We're going to revisit Euler's formula today, okay, just in the context of complex functions. Again, I wish to emphasize that the review that I'm recording for you today is just very tiny in scope. Okay, the subject of complex variables is ordinarily covered in a full semester course. So these lectures that I'm recording for you are not intended to be comprehensive by any means. It's not a substitute for the full course offered by the math department. My goal is to simply remind you of some essential concepts, things that hopefully have already been taught, and again, in the context of what we will need for ECE 3337. I'm not going to be doing theorems and proofs, okay? That level of rigor is not needed for our purposes, but that type of rigor is needed to learn the fundamentals, in a real math type of course. Out here, we're just going to focus on the practical essentials. Okay, so I'm suggesting that you get yourself a copy of some of these textbooks. I think they're pretty low cost and they're really good, and use them as a source of, practice problems, right? What I would recommend is that you set aside, maybe an hour or some amount of time every day, okay, to do some practice problems. So in part 1 of this review, we introduced the notion of a complex variable, and I want to remind you that these are two-dimensional things. These numbers have an x and a y, or an r and a theta. They live in a complex plane, okay, rather than just on a line, okay? The complex plane has a real axis and an imaginary axis. Okay, we call that, this is like our x-axis and this is our y-axis, and a complex number that lives in this plane is x plus jy. Okay, or z can be thought of as, an r and a theta. Now, Euler's formula is another formula that we introduced last time, which is e to the j theta, which is cosine of theta plus j sine of theta. It is one of the most beautiful formulas that I've ever seen, okay? It's right up there in my books with E equals mc squared. Now, in talking about complex variables, we need to be able to calculate the angle of a complex variable, the theta, right? We also call that the argument, and we can represent that as in a variety of ways, kind of like that, okay, or kind of like that, okay? And we're talking about this angle basically. Now, in calculating this angle, you want to go back and think about how it works, right? Now, if you just go by the simplistic formula that says theta is the arctangent or the tan inverse of y over x, right? That's not going to be enough, right? Because minus y over minus x is just the same as y over x, right? So if you have a number that's kind of like here, okay, it can get confused with the number z. So keeping that in mind, you have to calculate this argument carefully, okay, keeping in mind what quadrant the number shows up in, or if it lies on any of these axes, right? Now, we also introduced the notion of a complex conjugate. So z star is the complex conjugate of z, which is x minus jy. Okay. Now, for the most part, complex algebra looks and feels just like ordinary algebra, except you need to keep in mind what's under the hood, right? And on a practical basis, whenever you have a situation like this, when two numbers are getting divided, you need to watch for zero denominators, because when the denominator is zero, denominator, right? So whenever the denominator is zero, then the results of a division are meaningless. Now, in talking about complex variables, we, in the previous class, talked about a few special types of numbers. A number that lives only along the real axis, or the x-axis, okay, is said to be purely real. And for a purely real number, okay, the y is zero, right? It just lies on this line. Now, a point that lies along the y-axis is said to be purely imaginary, and correspondingly, okay, x is zero for such numbers that are purely imaginary. Now, finally, if you have a number that's pure, right in the middle of all this, which is the zero, right, then it has x equals 0 and y equals 0. Okay. Now, if you think about the polar representation of 0, clearly the r, which is the length of this line, is 0. But this angle can be any which way and you get the same answer, right? So for that reason, we say that the theta for 0 is undefined. Now, as we have spoken about the concept of a 0, we need to look at the other extreme and touch upon this notion of a complex infinity. So if you have the complex plane like this, okay, this is the real axis and this is the imaginary axis, okay, and there's point z, and here is the radius to that, and here is the theta, then people wanted to know, what does infinity mean in a two-dimensional space? See, if you're looking at just a one-dimensional axis, we know what infinity means. It's a point that's really, really far away. Okay, and to be precise, it's a point that's farther than any other point, that faraway point that you can think of, right? And the same thing along this axis. But how do you consider the notion of infinity in a plane? Now, this famous mathematician Riemann actually provided an answer to that, which is, I think, very, very elegant. You can think of it in terms of what's called a Riemann sphere, right? You put a sphere on top of the plane that straddles it, and then you can sort of project the north pole of that sphere to points far away. But you know what? For our practical purposes, think of infinity as a point for which, okay, r tends to infinity. But then just like for 0, okay, the theta is undefined, right? So a point at infinity is just far away from the origin, basically. Okay, and that's one, simple-minded way to think about it, and just for the purposes of this class. Now, complex variables are, used to represent all kinds of interesting quantities. Okay, we use complex variables to represent signals. Okay, and I might call that x of s, okay, where s is a complex number. And a little bit later in this class, we're going to represent this as sigma plus j omega. Okay, And then we're going to represent systems using complex notation, and we're going to call them, say, h of s, where s is the same thing, right? And the output of a system is another signal. So x of s would be an input signal, and y of s could be an output signal, right? Now, one of the things we're going to see is that many signals of interest to us, okay, can be written out as either polynomials or ratios of polynomials, right? And a polynomial function, okay, p of z, okay, looks like this: a0, which is a constant term, plus a1, which multiplies the first order term, plus a2, which multiplies the second order term, okay, and so on, all the way up to an z to the n, right? Now, one of the things we're going to find is that we'll have to deal with ratios of polynomials quite a bit later in this semester. Let me give you a little bit of a preview of why that's going to be useful, right? So a complex function can be thought of, okay, so suppose I have a complex function p of z, then you can think of it in the language of inputs and outputs. So the input to this function is z, right? And what it puts out is p of z, right? Let's call that w, right? So in the same language, what we're going to do is that we're going to be talking about systems. Now, a system's input is x of s, okay? The function that defines the system is h of s, and the output is y of s, right? So what we're going to find is that we'll be able to write down a formula that looks like this. Y of s is x of s times h of s, okay? Which means that h of s can be written as y of s divided by x of s. So we're going to have to deal with this ratio of functions, okay? And a lot of the time, this ratio of functions will turn out to be a ratio of polynomials, okay? It'll boil down to that, right? And of course, as always, we need to worry about when this guy will go to 0, right? So when x of s is 0, okay, the response is going to try and become very large, kind of like infinity, right? And for that reason, we'll call it a pole, okay? And it's very intuitive because, a pole looks like, a very tall pole looks like, something reaching out to infinity towards the sky. So, and then when y of s is 0, okay, we're going to call that as 0 because the output is 0. Now, in this course, exponential functions are going to be very important for us. We'll get a better feel for them, when we get a little farther ahead. But for now, take me on trust, and let's just first figure out how to deal with exponential functions. Okay, these are going to be exponential functions of complex variables, right? So if z is a complex variable, then, okay, e to the z, okay, is a function of this complex variable. Okay, now if z is x plus jy, then e to the z is e to the, x plus jy, right? Which is the same as e to the x times e to the jy. Now we can use Euler's formula on the second term, okay? And we can write it as e to the x times cosine of y plus sine of y. Sorry, j times sine of y. Now, these functions behave very much like their real counterparts. So if I have two complex numbers, z1 and z2, then e to the z1 times e to the z2 is going to be e to the z1 plus z2. Okay? And if I want to divide these guys, e to the z1 divided by e to the z2, then it's going to be e to the z1 minus z2, and of course, we better watch this denominator. Okay, so the trigonometric formulas work the same way for complex numbers, and it's largely because Euler's formula works for complex numbers too, right? So if you have, cosine of z, okay, it can be written as e to the z plus e to the minus z divided by 2. Now, similarly, sine of z, okay, is 1 over 2j e to the z minus e to the minus z. Right? So if z is e raised to some number w, okay, then we say that this is the same as saying or that w is the logarithm of, what am I doing here? Logarithm of z. Okay? Now this is called the natural log because it's defined with respect to the base e. Okay, so e is the base for this system of logarithms, and it's considered to be or called or referred to as the natural logarithm. So logs of complex numbers behave much the same as logs of real numbers with respect to some of the most common properties. So if I have the logarithm of a product of two numbers, right, then this is the same as, log of z1 plus log of z2. Now, a very common mistake that students make is, trying to say log of z1 plus log of z2 equals log of z1 plus log of z2, and man, this is wrong. Let me cross it out many times. Okay, don't make this mistake. Okay, the log of a product expands to the sum of two logs. Okay, but the log of a sum cannot get expanded in this manner. That property doesn't work. Similarly, the log of a ratio of two numbers, z1 over z2, is log of z1 minus log of z2. Of course, the usual caveat that we need to keep in mind is to make sure that z2 is not 0. Now, we can also work with logarithms in polar coordinates. Okay, so if the number z, is written in polar form as r e to the j theta, then we know that this is a periodic function. Okay, and the period is 2 pi radians or 360 degrees. Okay, same thing. So we can always write the natural logarithm of z as the log of this product, right? So it's log of r plus the log of e to the j theta, and the log of e to the j theta is just j theta. But one of the things that we can keep in mind is that this original guy is the same as e to the j of theta plus any multiple of 2 pi. Any integer multiple of 2 pi. Now, if we have that, then basically we keep in mind that this becomes theta plus m 2 pi. So the logarithm of a complex number is multi-valued. For every different value of n, you're going to get a different answer here, right? Of course, the case when n equals 0 is often the case we're most interested in, and we call that the principal value. Now, a complex function, let's go back to some of the language we developed a little bit earlier, can be thought of as a processor, right? Think of it as a box. So you got the function f, and what goes into this, or the input to this box, is z, and what comes out is w, which is f of z, right? So if you think of it this way, then what comes out is a complex number. And what goes in is complex, right? So this is a complex function. Now, since the output is complex, we can write this as a real part, which is u of xy, where z is x plus jy, and plus jv of xy. Right? Now, this can also be written in polar form, in much the same way, okay? And in that case, we would write f of z equals u of r and theta, and plus j of v of r and theta. Now, keep in mind that these are not the same, okay? So in other words, these u's and v's are different. And for the most part, that doesn't cause any confusion at all because we're going to be using one or the other. But if you plan to work with both of them at the same time, then you might want to give a different notation here. Maybe put a little subscript that says it's a polar form and there's a Cartesian form or something like that, right? So if you're only going to be using one of these, this notation will work fine. If you want to use both of them together, then try to come up with some extra notation to deal with that. So to summarize, the most common complex functions that are needed for our purposes in this class, okay, are largely well behaved, okay, and they also behave like they're real cousins. Now that doesn't mean by any stretch that every complex function is well behaved, right? There are a lot of badly behaved functions out there, and dealing with them entails more complexity or more complications. Let me use that word. And the second thing that we talked about today is the notion of a complex zero, right? A complex zero is a number that's at the origin. Its magnitude is 0, but its angle is indeterminate or undefined. Now, we also talked about the notion of a complex infinity, right? And again, this is a number that's far, far away from the origin, and it has an undefined angle. Now, I've taken a very kind of, informal view of these functions and these concepts in this video lecture. If you want to get a deeper understanding or a more rigorous treatment, you should go back to your math textbook and or go to the math department and take one of their courses on complex variables. Okay. Again, I want to emphasize that math is just like sports or dance or something like that, and it requires a daily workout, right? So just make sure to make some time for a daily math workout, maybe first thing in the morning, right? Soon after coffee. It's not a spectator sport. It only comes from doing. So you literally have to put a pen to paper and start writing things, right? And that's when things start to sink in into the mind. Try to focus on the fundamental concepts in math, okay? And try to just make sure you understand them. And keep asking questions or keep reading up the books. And sometimes you may have to do it more than once, and that's totally okay, okay? But just make sure to review the fundamentals, because if you get the fundamentals in mathematics, and the fundamental rules are relatively few in number, right? If you get those, everything else just becomes easy. And sort of vice versa. If you don't get the fundamentals, then you're going to make a lot of mistakes, and it's not going to be fun. Okay, thank you, and I hope to see you in the next part of this 3-part video lecture.